Good morning. My name is Krzysztof Rona. I'm happy to welcome you here on the HDF5 user meeting in Europe. I hope you are ready to go already Monday morning, but I'm sure Anton will give us entertainment at the beginning. So yeah, let's start just.
Okay. Aha, we have audio. This is good. That was switched off. Hi, I'm Anton Barty. I'm here from DESY, and I'm in charge of the scientific computing group for photon science at DESY, which is a big and a small part of the research that we do here, but a very important one. And HDF5 is quite close to what we do because one of the standards we use for the photon science community builds on top of HDF5. We've used it a lot. The European XFEL uses HDF5 as its main data format, and we try to wring as much out of it as possible and use it not just as the PDF for data, the most interchangeable one, but actually try to skip intermediate things. But to start off with, what is DESY all about? For a couple of you in the audience already know this, but those who've traveled a little way won't. We're located here in Hamburg, just on the other side of the Elbe River. So if you orient yourselves and walk down to the river, on the other side is one of Airbus's main manufacturing plants. They make the A320 series there, and they used to fit out the A380s as well. So it's fairly large. It's one of the old aircraft works from earlier. So we've got that just across the river, but just up here on the northern side in this parkland, in what used to be farmland, they built a research laboratory for accelerator physics and high energy physics. We've been here about, you want me to do this? I'm not sure this one works because this is one of these digital pointers. That one does. Great. Yeah, thanks. And so, yeah, up here, just up in this corner where you are at the moment, those of you who arrived, the airport is somewhere up here, and you've got the train station down here. This is a nice harbour area that's being developed. And here in this parkland, 60 years ago, they started developing accelerator technology for accelerating particles, electrons, protons, all sorts of things, to bring them up to higher energies for fundamental physics. And that's the sort of thing that we do here. Those who are online won't necessarily get to visit Hamburg and see the sunny weather we've put on for you. It's always like this here, at least in May. But yeah, so there's a couple of points here. One is we've got technology in Hamburg. It's a big commercial town, but there's also a lot of technology going on. And there's this massive research infrastructure that we've got here. DESY itself has about 3,000 employees working here. But it actually spans over. We've also got a remote site in Zeuthen. When the reunification happened of Germany, we joined up with a laboratory just outside of Berlin. And over there, they do astroparticle physics. So they look at the stars. And it's once again the extension of the particle accelerators. When you can no longer build them on Earth, you start looking to stellar objects to create the particles that you want to understand the basic fundamental nature of matter. And the fundamental nature of matter is also what goes on in our bodies, in atoms and proteins and materials and things like that, which brings together DESY as being one of the German hubs for researching the nature of matter, both at a very fundamental particle level and also how it works in applications, but also fundamental science aspects of metals, crystals, proteins, that sort of thing. Okay, so we're trying to do a lot of research that has not only fundamental importance, but also goes out and impacts on societal challenges. So if you were to jump up a little bit from this building, this is what DESY looks like here. We're sitting in this little building here, which is on top of the flash hall. Now, I'll tell you what all of that is. So you will have found the entrances to the building somewhere. And if you find that navigation around the campus is a little bit difficult, there's two reasons for this. One is there's a lot of building works. So even those of us who work here have difficulty sometimes getting to the canteen because day to day it works. Sorry about that, there's not a lot we can do, but it shows how vibrant things are here at the moment. And then there's this big ring here. It's 3-point-something kilometers in diameter, or in circumference. And this has been converted into one of the highest energy X-ray sources available in the world. There's a few high energy, so what you do here, I actually have to back up a little bit. DESY started here with a small little accelerator, a Doris, a little accelerator here, relatively small, and then it built this ring as a booster to actually a larger particle physics ring, a Hera experiment that goes under the parks. It's got several kilometers circumference, and it had detectors the size of this room, and those were buried under the parks. And you can still see that if you go down in these halls here, that this ring was a booster for it. But anyhow, you've got this infrastructure here, and what we've done is we've turned this into one of the brightest X-ray sources, because when you accelerate a electron, or go back to your high school physics, when you accelerate an electron in a magnetic field, it wiggles around, it bends, and as it bends, it actually gives out light. So it loses energy as it turns the curve, and it turns it into light emission. Now, depending on a formula I won't go into, with the strength of the magnetic field and the energy of the electrons going around, you get light that can be in the visible. It can also be in the infrared. That's where it started off. But if you push up the energies and increase the magnetic fields, you get up into the X-ray regime. So what we do here is, in similar wavelength range to what you get at your dentist or your at the doctor, but it's much brighter and much more coherent, which means that you've got a lot more X-rays coming through in it's much more spectrally pure, it's much more collimated, and it's much more intense. So you can do all sorts of research that you simply can't do in the laboratories. Okay, so that was one of the this facility here serves materials and science and everything around here, with about 20 beam lines stacked around on this ring. We've currently got plans to improve it even further, to make the beam even smaller, because the smaller you make the source, the more coherent you can make the light, the brighter and more energy you can get out, and the better you can look at your material. So we're working on an upgrade project at the moment. And if you were to look at it, I'm actually standing about on top of the ring at the moment. It goes about like this, and it goes round the campus. And this also means it's a bit hard to walk around, because there's this big berm here. You end up with radiation in there. You've got to have a lot of radiation shielding. So you end up with this large berm here. And that also means that if you want to get from the inside to the outside, it can be a bit tricky. But yes, we're standing here in this building about on top of that ring. And if we go just a little bit this way, you'll find the Petra Hall. It's open. If you go out this door, though, you see something different. It's flash, which is a free electron laser. And I'm also standing on that tunnel. It's that tunnel that goes in this direction. And instead of sending the electrons round in a ring in circles, what it does is it generates very short pulses of electrons in a straight line and then throws them away. Okay? So this ring sends the electrons round and round and round, and they reach a stable sort of situation. What you do in the linear accelerator, you create extremely short bunches. They're only about femtosecond durations long. And if you think of the number of zeros in there, femtoseconds are really short. They're about the time scale of atomic vibrations due to thermal motion, to give you some idea. Okay, so you can start to freeze thermal motion, you can start to freeze chemical processes. And the accelerator technology that was pioneered here at DESY, the superconducting, enables you to produce these short pulses in a really short distance, because the physics is it's got a really high field gradient, so you can accelerate the particles really fast, and you can create really short bunches. And then you use the same technology as for the ring, but you make a much longer magnetic structure, and you can get femtosecond duration pulses of X-rays that are nearly coherent. Okay, so they're really bright, they're really short, and you can do single-shot measurements with them down on the time scale of atomic vibrations and chemical processes. And we use this to literally take photographs of reactions in process. Okay, so that's what we can do with single shots. So it's really nice technology. We're standing right on top of it now. And if you look out there, you see a small little fan of beam lines. This flash gets up to about 500 electron volts. Okay, what's that? visible light's down around about 30. We start talking about energies. The wavelength of light down there gets down into the nanometer regime. So visible light, we talk about 500 nanometers to 300 nanometers. Light is on the blue end of the spectrum. And that, from lenses, actually kind of limits the resolution that you can get. If you want to get high resolution, you need to pretty much match the wavelength to the size of the feature you want to look at. So if you want to get down to nanometer resolution, you need nanometer light. If you want to get down to interatomic bond distances, you need to get down to angstrom light, and angstrom light, 1 angstrom is 12 keV X-rays, so you need to go to X-rays to study molecular displacements. So flash, on this distance, we could only get down to about 4 or 5 nanometers. And we wanted to get to these X-ray distances. So what we did, where Christoph is from, we built a tunnel here that's 3 kilometers long that goes out into the paddocks in the next Bundesland, okay? And out there, we accelerate electrons to about 12 GeV, that's just a number, but we can produce femtosecond duration pulses of X-rays with more than enough energy to burn through metal, okay? And we do experiments out there. It's the European exfil, where Christoph comes from. So we built on the technology, superconducting technology here. There's a liquid helium plant over there that produces the liquid helium, and then we send the electrons out. They've got magnetic structures that are 100 meters long, aligned to within micron precision. So there's a hell of a lot of engineering in this to make it happen. But it's a HDF5 users meeting, and what do? They end up saving the data. The experimenters come, they want to use the data, they don't want a custom framework, they want good data, so they come and do this. What this is doing is really just, it's the directorate, we've got a new director, Beata, we've got here, Wim. Really, the people probably not so interesting to you, but what you see is we have an entire division devoted to making these accelerators that help us produce these light sources. We have particle physics, which used to be done on site, but now most of the particle physics is done down in CERN, in Geneva. Okay, so we partnered up with CERN, heavily involved in the ATLAS experiment and the CMS experiment, 2 of these big, more than building-sized detectors down in CERN. And actually, DESY has for a long time been one of the main data centers. CERN has a structure where the main data gets saved at CERN, and then it's farmed out to all the collaborators. And DESY is one of the major tier 2 sites down, storing petabytes of data and providing compute capacity to the compute grid for CERN. So that gives us a lot of the computing backbone here, that astroparticle physics, which is out in Zeuthen, are now responsible for managing the data from the Cherenkov telescope array. So they get into telescopes that look at the sky plus satellites, and then you need to manage that data and make it available to the research communities. So data's huge out at Zeuthen in astroparticle physics for making this large infrastructure data available to the scientists. And then, of course, here in photon science, I just described the facilities because I'm from photon science. I can talk probably all day about that. But we also have users who come from everything from academia to industry, and we have the large-scale infrastructure here. We have to get not only the beam onto the sample in the right way, but then we have to get the information out of the sample onto detectors, and off detectors onto disk drives, and then off disk drives into computers rapidly to turn it into the knowledge that you want. And that's where this whole HDF5 business comes in, because we want to really make the data as accessible as possible to as many people as possible. So the point of this is not so much all of the directors have been changing, but that across all of the activities here, we're driving at making data on materials available to the community. And turns out the file formats are critical to doing that. This is just a bit of a timeline. As I said, started off in 1959, and then you had a few synchrotron rings coming up, the particle physics experiments, HERA, FLASH, and then the European exfil. Just recapping the same thing. And there's just a few photographs of the large-scale research infrastructures that we have. Increasingly, we're partnering with the universities. We're getting experts on site. So we have a Centre for Structural Systems Biology. We bring the biologists on site so they can use electron microscopes and X-rays at the same time, take the samples from one facility to the other, get the cross-sharing of information from different fields. It turns out we start taking detector alignment codes. When you have a big detector like Atlas or CMS, you need to align where all these custom elements are. So we have people who both can make detectors and analyze the data. And it turns out when you've got X-rays, well, certain bits of the maths happen to be just the same, and certain bits of the detector technologies happen to be the same. So you pick up and you have this synergy between what's being done with the particle physics stuff and the photons. So if you're careful not to silo yourself, it can get really interesting here, okay? And that, I think, is about where I want to end up. The rest of this is just, yeah, that's stuff that we did on ages ago. Okay, yep. So we're kind of known all over the world. We're heavy into the data things. And with that, I think I can hand over to the rest of the meeting and say, we really look forward to seeing this. A lot of us, because we have to interchange data with our experimenters, we really lean on HDF5 as an interoperable standard. We do sometimes run into problems with using it in certain ways. Performance, saving petabytes of data into it, not only in terms of volume, but speed of access becomes an issue. Also, some of the simultaneous aspects of can you write the data and read it at the same time are two issues among many that we come up with. So it's great to be at the cutting edge of this and have you on site here where you can see how we use it, not just for saving little PDFs of data to share around, but actually on a massive scale. So with that, I think I'll hand over to Christoph for the rest of the meeting.
Thank you, Anton, for the very nice introduction.
Okay.
If there is any urgent question, I think we have time for one.